Welcome back to the class. Let's quickly continue with module 2.0, Simplified Schrodinger equation, Chemistry 411, Physical Chemistry 3. I call this Simplified Schrodinger equation because we're not going to go into deep Schrodinger equation. It is somebody's duty to do that. I'll just show you how we arrive at Schrodinger equation using hydrogenic atoms. We're not going to go into solutions to the Schrodinger equations, particle in a box, barrier tunneling, and so on. Somebody will do that, but if you on request want us to do a video on that, a lecture on that, we can also do that to help you out. But that is covered by another lecturer. So we're going to go into just the simplified Schrodinger equation. The outline, we're looking at hydrogenic atoms, classical expression of the hydrogenic atoms, quantum expression, we look at the Schrodinger equation, and we'll conclude. The hydrogenic atom. The hydrogen atom has a proton and an electron. Like I said in the last lecture, the one electron is in the 1s atomic orbital. I hope you still remember your electronic configuration. For the hydrogen atom, we have 1s1. When a hydrogen molecule is formed, there is an interaction between the two electrons in the two hydrogen atoms. If in the hydrogen molecule an electron is lost, we obtain the ion. Look at it, hydrogen molecule losing an electron, so we have hydrogen molecule ion. That is this. All these are what we call hydrogenic atoms. Now for the hydrogen molecule ion, this is a proton, this is a proton. The separation between the proton is capital R. This is the one electron. There's an attraction between this electron and proton. There's an attraction between this electron and proton, but there's a repulsion between these two positive centers. Now it's easy for us to use hydrogen molecule ion. If we had used hydrogen molecule itself, it means that this electron will have another electron here, and then we are going to have another force here, repulsive force here, we'll have another one here, we'll have another one here. That is, we're going to have 4 centers all through, and the number of forces acting on this center will increase. But here we just have one here, and one here. So we'll use these to solve for the Schrodinger equation. Therefore, hydrogenic atom or hydrogen-like atoms is any atom or ion with a single valence electron. These atoms are isoelectronic with hydrogen. Except for hydrogen atom itself, which is neutral, these atoms carry positive charge, Z minus 1, where Z is the atomic number of the atom and E is elementary charge. The hydrogen atom is the simplest of all the atoms and consists of a single proton and single electron. In addition to the most common form of the hydrogen atom, that is called protium, 2 other isotopes, of course we know that deuterium and tritium, also exist. We just want to mention this so that you take your brain back and remember some of these things. Now look at the structure of the hydrogen atom. In fact, we have tried to bring this up here for you to understand the shielding and de-shielding regions. Applied force, look at the applied field here. Now you see how these forces go. The shielding region, we have our hydrogen. Look at the bond, there's a bond here. Look at another shift for another bond here. So all these forces gives us, there's a one hydrogen here, one hydrogen here. All these shows us, in 3 dimensions or in space, how there could be a shift or positional shift for the hydrogen atoms to show the field forces or shielding and de-shielding region. If we use that hydrogen, we are going to look at expressions. First is a classical expression. Total energy is so many forms: electronic, translational, rotational, vibrational, and so on. But the electronic energy is due to repulsion, that is between the two protons and the nucleus, and the attraction between the nucleus and the electron. Remember the triangle we drew? There's a repulsion between the proton, attraction between this proton and neutron, attraction between the other proton and neutron. I mean electron, proton and electron, sorry, not neutron. So we now look at only kinetic energy plus the potential energy. And in x direction, kinetic energy will be half mx squared. You know, v squared here is replaced by x because the velocity in x direction, plus the potential energy in the x direction. But if we want to look at the three dimensions, it's going to be half mx squared plus half my squared plus half mz squared plus the potential energy in x, y, z direction. Now, but momentum is mass times velocity. Now, if we square both sides, it will be p squared is equal to m squared x squared. If we square this equation. Now, let's make mx squared the subject from here. It will be p squared divided by m. If you remove one m here, x squared, you have this. One m will be remaining. So this divided by 1 m. We now substitute mx squared in equation 1. Look at mx squared. So instead of saying half mx squared, we're now saying half p squared over m. So that is p squared x divided by 2m. Also plus potential energy in direction of x. This equation 2 is the classical expression of our system. The classical expression for the energy of our system. We want to find the quantum expression. So we need to find a mechanical approach, in which case we replace the momentum term with the operation for momentum. Remember your vector, momentum is a vector quantity, so remember treatment of vectors in the x direction. The coefficient for the vector is I, and I squared is equal to -1. Remember your elementary vector treatment, I times I equal to -y, you know, ijk for xyz. So we're interested in I, that is for x direction. So we now put from equation 3, we now have px squared, that is our operation for momentum, will give us this, which is equal to this equation here. So we substitute for p squared in equation 2. E is equal to, remember, we'll now substitute for p squared here, and we'll have this equation. Then we can simplify by moving this Vx over to the other left side. We'll have E minus Vx equal to all this thing remaining here, minus h squared del squared divided by 8 pi squared m del x squared. If you look at this, remember your mathematics, dy dx, something is missing here. Where E is the total energy of the system, Vx is potential energy. This is an instructor. This is an instructor which tells us to do some operation, and it's called the differential operator. There's something here, it's telling us to operate on something. Well, that thing is not there, we've not written it. And the wave function is called the operand. It is the wave function that is supposed to be here. So this operator, differential operator, is carrying out a function, second order function on this wave function. Therefore, the complete equation is given as this. Look at it, we have included that wave function, which is here, giving us this. So the total energy E is the minimum energy of the system. If energy is not minimum energy, then is energy of excited state. Equation 5 is the Schrodinger equation. We describe the motion of electron as a wave in one direction, in just x direction. Now for 3 dimensions, we now bring in all the 3 dimensions, and then we have this wave function in xyz direction and potential energy in xyz direction. This is the Schrodinger equation in 3 directions or 3 dimensions. And this is Schrodinger equation in only one x dimension. We can also have this, instead of using partial differentials, we bring all the del x, del y, and so on partial differentials together, and we use this symbol here, and we call that Laplacian operator. This is Laplacian operator. So if we can rearrange that equation, we'll get this. If we rearrange again, we'll get equation 7, and we have this, we call this is h, but not normal h. Phi is equal to E phi, where this h gives us the equation, and we call it the Hamiltonian operator, whereas phi is the wave function and E is the total energy of the system. So this gives us a shorthand of the Schrodinger equation. Okay, this is a very short video. Thank you very much. Like we said, simplified Schrodinger equation. We have looked at hydrogenic atoms, looked at the classical expression for the hydrogenic atoms, looked at the quantum expression, and derived the Schrodinger equation, the simplified Schrodinger equation in one direction and in 3 dimensions. Thank you very much. See you in the next class.